Hello everyone, I'm Sri and this is my lab for Circuits Lab Report and this is for Physics 2212. For the introduction of this lab, we have that the purpose of this lab is to use charge and energy conservation principles to predict the behavior of circuits containing different resistors and capacitors. Some of the physics concepts we'll be needing are loop and node rules. Node rule is shown to the top right, while loop rule states that the sum of the voltages in any closed loop must add up to zero. We also need the conservation of energy law, the conservation of charge law, the RC formula, which is shown to the right, Ohm's law, which states that V equals IR, voltage equals current times resistance. So for the model and the preview of results, the system is the circuit, the surroundings are everything else, and an assumption that I made is that the resistance of the objects that make up the circuit are negligible, and a preview of results is that the RC value is close to 6 seconds. So for part one, which is the charge conservation and energy conservation in series circuits part, to answer some of the questions that were asked in the instructions, first I predicted that the first current and the second current will be the same, and that I knew according to the loop rule. And when the ammeter was reversed, it showed the negative value but same magnitude. And when the black probe of the voltmeter was connected to the batteries, the voltmeter read the sum of the voltages of the batteries, which is shown in the top right picture. And when the voltmeter was attached, the circuit was open, so the ammeter read zero, which we could also see in the top right picture. So these are some of my potential difference measurements. So first, we already know that the current is 0.02 amps because that was shown on the ammeter. And we also know that the sum of the potential difference values should equal zero because of the loop rule. So when we add these potential difference values, we see that they equal zero, and this satisfies the loop rule. So this is the graph of potential difference versus position. So based off the values that we found in the previous slide, we were able to make this graph. So now to answer some of the questions asked in part one, when you attach the voltmeter, you alter the circuit. Why doesn't the ammeter reading change? The voltmeter has high resistance and low current passes through it, so the reading on the ammeter does not change because current is not affected. And now the second question, which is, now replace the voltmeter with an ammeter in parallel with the hundreds ohm resistor. What happens to the current through the other ammeter and why? And when the ammeter is attached in parallel, the current flowing increases to 0.06 amps because the ammeter has zero resistance, which was one of our assumptions, and the current avoids the 100 ohm resistor. So now on to part two, which is the RC circuits part. So first, we were given two situations, the first one being a bulb and capacitor attached in series, and the other being a capacitor directly connected to a 10 ohm bulb. And in both situations, the light was bright but slowly dimmed until there was no longer any light, and the current starts off with a large value and eventually dropped to 0 amps. And the time it took to discharge for the 10 ohm bulb was approximately 10 seconds, and for the 20 ohm bulb, it was approximately 19 seconds. So this is a table of values and a graph. And for the table of values, I used a stopwatch and used the simulation to find these values. And then I found the linearized version, which is the third column of the table, to make the graph to the right. We can use the slope and the RC formula that I showed in the introduction slide to calculate the RC value. So these are my RC value calculations both experimentally and computationally. So first, using the experimental data and the slope that I found in the previous slide, I set the slope equal to -1 over RC, and I found the RC value equal to be 6.02 seconds. Next, I used the formula to compute it and found that the RC value was 6 seconds, and comparing those two values, we see that they are very similar. So to conclude, we need to answer the what if questions. So for the first what if question, we know that in real life, an ammeter has a small amount of resistance, while in the virtual model, we assumed that it had no resistance. So in real life, the current readings on the circuit would be slightly lower. And for the second what if question, on the simulation, the capacitor charged immediately because of the assumption that we had no resistance throughout the circuit. But in real life, the objects that made up the circuit have some small values of resistance, so the capacitor wouldn't charge immediately. So for some sources of error, there could have been a timing error. I could have hit the stopwatch too early or too late for some of the trials, and there could have been rounding errors. And also in the virtual model, we assumed that objects that made up the circuit had no resistance, and we know that isn't true in real life, so that could have contributed to the error as well. Thank you for watching my lab report for Lab 4.